Next thing that I want to mention about is gamma. So if you've messed around with the controls on your graphics card or your display, you've no doubt seen this. So what is gamma? So here's a picture. If we adjust gamma down, you get a picture that looks more like this. You adjust gamma up, you get a picture that looks more like this. This just looks like image editing. Yeah, sort of. But what's going on here? So there's a transfer function in my display. So your display is digital now, but this still applies. This picture makes more sense if we think about sort of the way CRTs work. We insert a voltage in the bottom, and a voltage in the back of our display. Some analog nonlinear process happens to generate electrons based on this voltage, and then some nonlinear process changes those electrons into photons at the phosphors, right? And something comes out. So the question is, does it look like this, right? I put in a voltage, I get some number of photons out, and that thing's linear? Or does it look like something else? What's this curve look like? So it turns out on CRTs, the curve looked like this. So you put in voltage, and on CRTs, right, you get increasing intensity. And this is a gamma curve of 0.25. So this is you don't have to know this function, but this is what came out. There was a black level. This is the voltage. This is the voltage back level. There's a symbol here, gamma. So this is where gamma came from. It's because in this original equation there was a gamma symbol in here, and this is a gain. So, and we had knobs on our TV. It's a little bit different now, but this notion of gamma has survived, right? It originally got here from our CRTs, but it's survived, and we still have it. Now, why does this thing work? Okay, back to human perception. So human perception is the inverse curve of this, practically. You put intensities, and our perceived brightness actually falls off. Twice as much intensity you do not perceive as twice as bright. And this applies to other things: smell, taste, length. Length we perceive linearly. Everything else has some kind of curve to it, if you go measure what people think. And this curve is kind of inverse of this curve. So that means that in terms of humans, if I put in twice as much voltage, they think it's twice as bright, if I combine these two curves. So we built systems that work like that because it kind of worked for the human perception system. Computer graphics would like it if the world was linear. And we'll see some examples of why, but it would make all of our math work nicer. So what do we do, right, if we want to do this mapping between these things? So we have some incoming values, and we don't perceive them linearly. Okay, so for most of you, the step from 0 to 0.1 should look like a big change in brightness. And the step between 0.8 and 0.9 should look like a smaller change in brightness. What we really wish was the step sizes seemed kind of the same. We kind of wish that from the 0 to the 0.1 sort of looked like the same size step as, between these two steps. So this is a human perception kind of thing. This is now a linear scale coming out. It's through your monitor. Your monitor has unknown gamma. None of this is perfect. So it's not a perfect visualization. But I want to make the point that our eyes don't perceive linearly. So why should we assume the monitor is? Well, why we want the monitor to be, consider this case. Here I've displayed 50% gray on the monitor. Here I've displayed every other pixel is turned on. So it's either black or white or black or white. Now, again, this is through Zoom, through whatever, so it may not actually be working that way. But the idea is this is black or white turned on. You wish these two colors were perceived the same. Like when I squint, this brightness is perceived the same as this brightness. That's only true if we have a linear response. This is the 3/4 and this is the 1/4, right? Just to have more comparison. So if I have a linear display, these things will all match. If I don't have a linear display, these things won't match. Now, why would I care? Well, if I'm starting to play funny games with all those subpixels and say, like, I wish it was true that if I turn on 2 pixels at 50% power, that's sort of the same overall brightness as 1 pixel at full power, right? That somehow those add up and produce the same thing in my computer graphics system because I'm playing low-level games with the light. It only works if it's all linear. If I have some kind of crazy curve going on in there, it's not going to work. So why do we still have gamma? Like, why don't we build displays where this stuff is linearized? Well, because most people are not playing low-level games. Most people are watching movies, and on movies, we can mess around with that gamma and we can make it look a little bit better. So we leave it as a user controllable thing. If you're a photographer or you're really into color science or you like to get these things right, most graphics cards have a way to go mess with the gamma table. And if you had a color correction device, you can go set this to be something precise. So your monitor exactly matches somebody else's monitor. And if you work in a movie studio, you can bet you do that. But for most of us, we don't mess with gamma. How do we do the mapping? There's just a lookup table. So my frame buffer says I would like to put out color 4, and the lookup table says, oh, change that to 32 for my current mapping on my monitor. So here's a low gamma, here's maybe okay, here's a high gamma. This is what you're seeing. These kinds of things are tuned around to control in your graphics card. You've probably seen, so I thought I should mention it. In computer graphics, unless you're doing movies or something, we largely ignore this. You haven't dealt with it in your code. I would say most people don't when they're building games. You may mess with it in your graphics card so you can see better than your opponents in your dark dungeon game, right? I think this is the place that most people are messing with it.